Here is Starfish graphical interface. Suppose I'm a user trying to diagnose a poorly performing MapReduce application. I enter the location of the profile store where the profiling data for my application has been collected. In this particular case, the profiling data consists of the job history logs for my application that have been collected in a directory in my local file system. I enter the path and click Submit. We can immediately see that the application consists of three MapReduce jobs. For each job, we can see the job's time to completion in seconds. The second job takes nearly 6 hours to run and is clearly the bottleneck in this application. Let's analyze this job using Starfish. Let's start with the settings view. This view shows the Hadoop job configuration parameters that were used for the job, the cluster resources on which this job ran, and the configuration of input data for this job. Let's start with the job configuration parameters because it is their settings that can have a major effect on job performance in Hadoop. For most of these parameters, Starfish does a comprehensive health check and gives intelligent recommendations. For example, Starfish points out that the number of reduced tasks used for this job, which was 4,000, is bad because each reduced task runs for too short a time and outputs too little data. Starfish recommends changing this value to a much lower setting of 66. As another example, Starfish identifies that the reduce slow start parameter for this job should be increased because early started reducers wasted up to 335 hours of cluster compute time that could have been better used. Starfish also points out other misconfigurations. For example, Starfish says that the combiner is not effective at all and should be turned off. These health checks and recommendations are designed to be robust and easily understandable. Now let's see why Starfish made these recommendations. Let's go to the timeline view to understand how map and reduce tasks in this job ran from the start to the completion of the MapReduce job. For users who are not familiar with how MapReduce and Hadoop works, this view is a good place to learn. What we see on the top is a job summary view. This job took around 6 hours to run. It has 6,000 map tasks and 4,000 reduce tasks, and totally used up around 3,100 hours of cluster compute time. Below that, we see a job execution timeline from start to finish. The blue boxes show the execution time intervals of map tasks, and the purple boxes show the execution time intervals of reduce tasks. Job execution is categorized based on the machines on which tasks for the job ran. The machine name is shown on the left side. We can scroll up and down to see how tasks ran across the different machines. Recall that Starfish suggests that there are too many reduced tasks, and we can easily see that there are many reduced tasks that run for a very short duration, but the early started reduced tasks that run concurrently with the map task, like these ones here, take much longer to complete than most of the later started reduced tasks. The starting reduced task early does not seem to be useful at all. Why did Starfish recommend turning off the combiner? We can see from the map task information that the combined output records is almost the same as the combined input records. Thus, the combiner is not helping with data reduction at all and should be turned off to save CPU cycles. We can observe that a number of map tasks finished much faster than the others. A common reason for such a problem is the presence of skew in data. Starfish provides a skew view to be able to enable the user to detect such problems easily. First, we can see the map input data distribution across all the map tasks. This distribution is captured by a histogram that groups map tasks by the size of the input data that they process and displays the number of map tasks on a binary log scale. For example, about 2 to the power of 12 or about 4100 map tasks process input data in the range of 20 to 55 megabytes, while there is one map task that's processing around 500 megabytes of input data. The distribution of map outputs is almost the same as the distribution of map inputs, since most map tasks generate roughly the same amount of output data as their input data. Interestingly, the distribution of map task running times is very different from the distribution of map input and output sizes. Thus, there is no clear relationship between the data size and the task running time. This means that the running time of map task is determined by some other factor. For example, the behavior of the map functions may be data dependent, or the load on the machines where the task run may be highly variable. Now let's move on to the reduce side. We can see that while most reduce tasks are processing less than 257 megabytes of input data, there are a few reduce tasks that process more than 2 gigabytes of data. Such skewed reduce tasks can slow down the overall job performance. Let's keep this in mind as we probe further. From the reduce output view, we can see that all 4000 reduce tasks generate less than 2 megabytes of output data each. This is a problem that Starfish identified earlier in the health check. Too many small output files from a producer job is usually bad for any consumer job that reads the producer's output. Since each small file will be processed by a single map task, the consumer job will end up having too many map tasks that are inefficient as well as can cause contention for map task slots in the Hadoop cluster. The last view is the distribution of reduced task running times. We can see that while most reduced tasks finished within 268 seconds, there are also many reduced tasks taking about 1500 seconds, which are likely to be those early started reduced tasks. In addition, one reduced task was running as long as 1 hour. It is likely the one with 3 gigabytes of input data. Hope that the job was not waiting for this long running reduced task to complete. Let's go back to the timeline view to double check. Let's see where that long running reduced task is. Here it is. When tasks of a job run on many machines in the cluster, in this case on about 4000 machines, it may not be helpful to show all the machines and tasks in the timeline. The Starfish selectively shows machines in an intelligent way. Indeed, we see that this reduced task that ran for an hour significantly slowed down the overall job. We can see that this task does have more than 3 gigabytes of shuffle input data. In its 1 hour of running time, this task took about 42 minutes to shuffle this huge amount of data. This problem of reduced skew may not be solved by tuning parameters such as increasing the number of reduced tasks, since this job already has too many small reduced tasks. Instead, the application developer will need to look at the data distribution and redesign how the map output data is partitioned across the reduced tasks. Starfish supports other types of profiling data and views to better understand and optimize the performance of MapReduce applications. Let's see an example involving a complex MapReduce workload that contains a number of jobs. For the jobs in this workload, more detailed profiling data than MapReduce job history logs was collected. This data enables us to see profiles and data flow views in addition to the timeline, skew, and settings views. What we see now is the profiles view, which shows a detailed time breakdown of subphases in the map task and reduce tasks. This view will help understand where the performance bottleneck is. As we can see, for map tasks in this job, most of the time is being spent in overheads such as serialization and spilling. Most of the reduced task time is spent in the shuffle phase. Using the data flow view, the user can see how much data was transferred between different machines in the cluster during the shuffle phase of the MapReduce job execution. Each vertex in this view is a machine where tasks of the job ran, and the thickness of the line between any pair of machines represents the amount of data that was shuffled between them. Hotspots can be seen from this view very quickly. An exciting feature of Starfish is the ability to replay the execution of a MapReduce job to debug any slowdowns or other variations in the job's performance over its running time from start to finish. For example, as we replay the execution of this job, we can see that it did not shuffle any data for up to 12 minutes of its 30-minute execution. From the skew view, we can see that this job produces almost 10 times more data to shuffle compared to its input data. Thus, having more map tasks and starting reduced tasks early may improve the performance of this job a lot. Recall that the behavior of this job is very different from the behavior of the previous job that we saw, where early starting of reduced task was undesirable. That was a quick tour of Starfish's Visualize feature. With intelligent built-in Hadoop expertise, Starfish helps Hadoop users optimize application performance quickly and easily, and to optimize resource consumption for better cluster usage. What's more, with a lot of raw data visualized in an intuitive way, Starfish enables Hadoop application developers understand MapReduce better, and it helps them leverage Hadoop and big data analytics more effectively. The Starfish team welcomes your feedback and would love to work with you to further evaluate and improve Starfish. We are passionate about applying big data analytics to make the entire big data ecosystem fast and easy to use. Please visit the Starfish research website at http://www.cs.duke.edu/starfish for more information. Thanks for watching this video.